My name is Jim Mattson. I work for Google, but I'm not here today to talk about something that I did or something that my team did. I'm here to talk about something the KVM community has been working on for a number of years, which is x86 nested virtualization. Only on Intel. I'm sorry if there are any AMD people in the audience. I only have access to Intel machines, really. And so that's what I focused on. Everyone knows that x86 virtualization, nested virtualization is slow. But the question is, why is it slow? And I think the answer is that no one has really looked at performance. We've been so concerned with trying to get the correctness right. And at this point in time, correctness is pretty much there. But the performance really isn't where it should be. And I think there's a lot of low-hanging fruit. And I hope to demonstrate in this talk that there is a lot of low-hanging fruit. And I hope to motivate you all to go out and find some of it and pick it and reduce the performance penalties that we're seeing. To that extent, I think my talk has already been successful because as soon as I proposed it, Paolo went out and found a very egregious function that he basically cut the overhead in half on with one commit. So already it's starting to pay off. I'm going to talk about specifically some performance profiling that I've done on a Broadwell machine, or I think that's 5th generation Intel Core processor, for those of you who are keeping track by marketing names. The processor has plenty of threads, plenty of RAM. There's no overcommit or anything at any level of the test. The distribution I used was Debian 8. That's in the VM and the nested VM. So that's L1 and L2 for those of you not familiar with the nested terminology. At L0, the software running on the host, there isn't really a distro. It's the Google internal distribution. But I did run the same kernel at every level. Not the kernel we run in production at Google, but 4.13.4, which is at least when I did the test, it was the latest stable release. And I did cherry pick that one commit from Paolo that greatly impacted nested VM performance, because I mean, he's already done that. So thought I'd include that as well. And it's in all the kernels, even though it only makes a difference at L0. You probably all know that we don't use QEMU at Google, but I use QEMU for these experiments, QEMU 2.10.0. And to compare, I grabbed VMware Workstation 14, which was just recently released. VMware has supported nested virtualization in Workstation for 5 years, I think. VMware Workstation 9 was the first release to officially support nested virtualization. So this will give us an idea of how we're doing in comparison with our competitors who have a bit of a leg up on us. I do have to note that I had to patch Workstation 14 to actually work on the 4.13.4 kernel because they're usually a little bit behind. And as usual, they were a little bit behind. So the first thing I'm going to talk about is a micro benchmark, totally bogus, concocted benchmark that is aimed to make nested virtualization look as bad as possible. And this micro benchmark is CPUID in a loop. It's the tightest loop I can make it. It's 4 instructions long. And I run this CPUID instruction in a loop for 30 seconds, then it's terminated by a SIG alarm, and I see, well, how many iterations did I get through, and what's the cycle count per iteration? The test environment that I've got described here, LLVM in this case is not a compiler, it's the lowest level VM. So when I do my L1 benchmarking, I'm talking about the lowest level VM being L1, and then when I do L2, the lowest level VM is L2. So I give the same amount of memory and the same count of CPUs at the terminal level of the test. So if I am running an L2 VM, then the parent has to be a little bit bigger so that there's no contention for resources. You might wonder, why did I use 15 vCPUs and 32 gigabytes of RAM to do this CPUID test? Well, you'll see I used the same thing for some other benchmarks later on, and it was just easier to have one configuration. So how do you think we do on the CPUID loop? Well, it's not great. L2 KVM QEMU is 25 times slower than L1. Not too good. And VMware Workstation clocks in the L2 is only 11 times slower than L1. So I think there's definitely some room for improvement in our nested virtualization strategy. You'll also note VMware Workstation kind of edges out KVM and QEMU at L1 just by a little bit, and so maybe there's a little bit of room for improvement there, but I didn't look at that level at all. Those of you who were in the ARM nested virtualization talk earlier today may recall that he talked about the problem of L1 kind of inducing a bunch of VM exits as it's responding to an L2 exit that is caused by L2. And so that's one of the first things I looked at, what I'm calling Ancillary L1 VM-Exits. So these are VM exits that L1 causes because it's processing an exit that was forwarded to it from L0 because L2 had a VM exit. And first I'm going to look at VM resume. So VM resume is L1 saying, okay, I want to go back into the L2 execution context. And you kind of figure, unless you get very, very clever, you're going to have one VM resume exit for every CPUID exit that is done by L2. And I'm going to argue that that's probably all you need, is that one VM resume exit. But we see that with KVM and QEMU, we have two VM read exits, one VM write exit, one xsetBV exit, one read MSR exit, all for that one CPUID exit done by L2. I'm not going to worry too much about what VMware does, but they do a little bit better. The xsetBV exit, I kind of think might be a leftover from the days when eager FPU could be false. I'm not sure, I haven't really looked into it in detail, but this is setting up XCR0 for the L2 guest, and it seems like that context ought to be L2's context as long as you're kind of in the vCPU run loop within L1. But we can look a little closer at some of these exits, the VM read and VM write and read MSR exits. I'll point out that the processor I was using, the Broadwell CPU, does have support for VMCS shadowing. And VMCS shadowing is it's a VMX capability that Intel introduced to help nested virtualization so that L1 can perform VM read and VM write operations without causing a VM exit. So if it can do that, why didn't it? And you'll see on the next slide that the problem was that L0, can confuse myself actually talking about all these different levels. L0 has a list of fields that it's going to allow L1 to VM read or to VM write. And some of these fields that are frequently accessed by L1 just aren't on that list. PML index and interrupt status basically are the cause of most of the VM reads. The other two here are pretty much inconsequential. And VM write, it basically looks like we write the VMX preemption timer on every round trip. So there's another one that probably should be in that list and isn't. And for the read MSR, It's kind of depressing. We read IA32 debug control every time we handle a nested VM exit. And I don't know about you, but I figure on my machine, debug control is 0, 100% of the time. So maybe I could do something about that particular problem. So that's it. Yes?
So the VM read and VM write, the list of the common egg, of the ones that were cached, was done on an older version of.
Yeah, I'll get to that when I get to my lessons learned at the end. But thank you for pointing that out, yes. As Paulo was saying, the VM read and VM write fields, this has to do with the list being generated a while ago and new features coming along and no one really monitoring what had to be done with that list to handle the new features. So I did a few macro benchmarks as well. I didn't do any real industry standard benchmarks, but I tried to pick a few different interesting cases that would exercise different subsystems. So the first one I did was Kernel Compile. And this was done with the same setup as CPUID. So at the lowest level VM, I had 15 CPUs, 32 gigabytes of memory. I took 80% of that memory and made a RAM disk, and then I put the files for building the kernel on the RAM disk. And then I timed how long it took to compile the kernel and all the modules. Now, it's actually quite promising, I think, to see that in this case, the nested VM on KVM and QEMU was only 4% slower than the non-nested VM. This is primarily a CPU-bound benchmark, so there probably aren't a whole lot of VM exits. And nested virtualization actually does really well here. Now, despite doing, pretty much blowing KVM out of the water on the little micro CPUID benchmark, Workstation fell behind here, and it was 7% slower than its L1. And I looked into it. When you get the slides in PDF after the conference, you'll see in the backup slides, I've got a big table of the VM exits that were taken by each hypervisor during these benchmarks. I would show it, but it's too small for anyone to read. But when you look into it, it looks like essentially Workstation is paying for a few things. One is there's no VMM exclusive for workstations. There's VMX on, VMX off, VM pointer load, VM clear. All of these things are causing VM exits. These are new sort of ancillary exits every time that the VMware equivalent of vCPU run, that ioctl exits back to user space. And they also seem to pay quite a bit for not actually living in coexistence with the kernel, right? So they have a virtual machine monitor that runs in ring 0 on its own page tables, with its own interrupt descriptor table, and everything else kind of completely disjoint from the Linux kernel. And it looks like the setup and teardown of that cost them quite a bit too, so that's why they fall behind. The next one I did was an iperf benchmark, and for this benchmark, I had 2 L2 guests, each with only 7 vCPUs and 16 gigabytes of memory. And I had the networking connection between the 2 L2 VMs so that no hardware networking or anything else was involved. This was entirely software networking. And here, there's a surprise that I actually still can't explain. Under KVM and QEMU, we actually did 10% better in the nested VM than we did in the non-nested VM. If anyone can come up to me after the talk and tell me why, I'd love to know. Workstation just, I don't know. So they don't have, I used VirtIO.net in KVM QEMU, and they don't have that in Workstation, but I used their VMXNet 3, which is sort of the equivalent, pair virtual network device. And I got the results I expected, I think, for comparing L2 to L1, but the numbers are just so abysmal. I think it's not even apples to apples. I have no explanation for why it could be so bad. And then the third thing I looked at was a benchmark called schbench. I wish people would put more letters in there so it's pronounceable. So this is essentially a scheduling latency benchmark. And I think it came out of Facebook, if I recall correctly. I'll let you know that all these numbers, L1 and L2, are really horrible. I didn't give the L0 numbers, but these are just miserable numbers. And you all know that sort of message passing workloads on a VM, whether it's nested or not, they're just not very good. Here, the nested KVM QEMU VM was 60% worse than the non-nested case. VMware started worse to begin with, but nesting was only 10% worse, and I think a lot of that, again, probably comes down to the reduced Ancillary L1 VM-Exits. But I think for kind of real-world workload, this is probably the worst case for you know, a real application on nested VMs, which is a 60% reduction in performance, or 60%, 1.6 times as slow, or whatever you want to say. So I wanted to look in a little more detail to see. I mean, okay, so we know it's bad in some cases, but I want to look at in a little more detail at why it's bad. And so I used perf, which is a great tool. You should all use it all the time. Every time you check something in, use perf and see what happens. Because then we wouldn't get into this situation, I think, where sometimes there's just these really easy pickings. On the CPUID benchmark, we can see the top hit here is nested VMX disable intercept for MSR. The next two you might kind of expect. Nested VMX run is the function that essentially handles emulating VM entry from L1 to L2. And VMX vCPU run is the function that actually does the VM enter from L0 to either L1 or L2. I've highlighted those in red because they appear on every one of these slides that I did the perf on. So those are generally fairly important. Some of the others here, copy shadow to VMCS 1.2. That's copying the state from the shadow VMCS that allows, which shadow VMCS is this? This is the shadow VMCS that L0 uses so that L1 can do VM reads and VM writes without causing a VM exit. I think as you add more things to that list that I was talking about earlier, this is just going to get more expensive. But it's not obvious that there's a lot to save there. Looking next at Kernel Compile, again, we have the three hot ones from before. And kind of a surprise to me was that QEMU spin lock slow path shows up way at the top. I don't think we should worry about this one. This is, I think, this is paravert spin locks. If you're up there spinning on a lock, you probably don't have any work to do anyway. So maybe it's not a big deal if that's way up at the top. iperf looks fairly similar to the CPUID, but read TSC kind of creeps up there a little bit. I think I looked into that, and it seems like pretty much on every nested VM entry, we're reading the timestamp counter. I'm not sure there's any way to save a lot there. And then the scheduling benchmark, again, QEMU spin lock slow path shoots up, as does underbar lock acquire. I don't know why that one's up there. But the three in red, again, show up pretty high. So I wanted to look at those in a little more detail. And so I used perf annotate to take a look at those particular functions. And we look at nested VMX run. I skipped nested VMX disable intercept for MSR, because I think that should just hopefully go away completely. But nested VMX run, the hottest thing in there is the loop that calls nested VMX disable intercept for MSR. And this all has to do with x2 APIC virtualization. That's unfortunate. The other thing that's very high there is the memset of the MSR permission bitmap that L0 is going to use when it's running L2. L0 has this idea of MSRs it's willing to pass through to its VMs. L1 has an idea of the MSRs it's willing to pass through to its VMs, and we kind of have to create the intersection of those permissions for L0 to run L2. And as part of creating that intersection, we first do this memset to say, well, okay, let's start with no MSRs being allowed, and then we'll take a look at the ones that can be allowed. In VMX vCPU run, we now get to see that debug control MSR right up there at the top. Notice that this is actually running at L0. So this isn't because there's a read MSR intercept. This is actually because we're doing a hardware read MSR, which is like an 80 cycle instruction or something like that. And so ideally, since the kernel set the MSR to begin with, it might remember what it set it to and just get a value out of memory instead of going and querying the MSR. The 23% VM resume and a couple instructions after, I think that's kind of what you have to pay. I mean, that's just the hardware cost of doing a VM enter. And then somewhere in there was the read TSC. I forget the context around there exactly, but I don't think there's much to be saved there. So some lessons that I would suggest taking away from this. One is continuously monitor performance. These VM read and VM write VM-Exits that kind of snuck in as we added new features but didn't update the VMCS shadowing lists. That should really never have happened, right? I mean, someone should have been monitoring the performance, and some red flag should have gone up and said, oh, wait, update those arrays to avoid this heavy performance penalty. We should avoid reconstructing that MSR permission bitmap. The memset of a 4K page plus this loop that we go through of 256 x2 APIC registers. And I have to believe that this bitmap is pretty much constant.
It's pretty much constant, but actually it's also like the big majority of it, it's really, really constant. Like, not pretty much, it is constant. We know that it is constant. So, like, of the 4096 bytes, there are 4000 that are always the same. And the other 96, we can just process them 64 bits at a time, not one.
Yes.
And we would still reconstruct it, but we will reconstruct it 64 times faster.
Right. So, I mean, use a little more cleverness, I guess, in reconstructing it. Be sure to use the VMCS shadowing effectively. That kind of ties in with the first lesson. And then cache that I32 debug control value in memory. Don't go out and read an MSR. You're acting like Microsoft when they went and read the TPR all the time, and you know what that did to virtualization. So just like Microsoft started reading the IRQL out of memory, if you've got something that's in a slow to access hardware register or whatever it's called, put it in memory so you can get at it quicker. And that's about all I have to say. So I'll open the floor for questions.
So for your iperf thing, where you had better performance for
better performance on iperf?
Yeah, that was a bandwidth thing, right? It wasn't latency back and forth. You were trying to measure the amount of traffic you could push through?
That was just iperf sending one direction. So I had a client and a server. It was traffic one direction, all virtual networking.
Right, so we saw something similar when we compared ARM and x86, and what we saw was that ARM improved where x86 decreased, and the reason was because ARM was slower in absolute terms compared to the line rate. You ended up getting fewer interrupts because you could buffer more data per interrupt, and that ended up improving your performance. So you might want to count the interrupts you see for your workload at the L2 level and compare those.
Okay, thank you very much.
Can I recommend a program called Super Nested? It runs nested, 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 nested until things fall over. And it gets to about L4 on my big machine at home.
Well, I think before I do that, I'm going to finish my implementation of virtualized VMCS shadowing for KVM, because that'll help get a lot deeper when you can start using VMCS shadowing below L1, or yeah, below L1.
I'm pretty sure that you tried to tweak some of these things already. Do you have any numbers how good you were able to improve there?
No, I haven't tried to tweak any of these things. These are all for people out there to pick up and start doing. These are easy things, and then we'll do round 2, and I think we'll be closing in on VMware pretty fast.
Okay, see you at the next KVM forum then.
Did you have data for Zen side?
Data for
Zen side.
Zen?
Yeah, because we enabled the nested in Zen before KVM.
I have no Zen data. Sorry. One more question? All right, thank you.